Hello bachcho, welcome to the class. So today we're going to tackle a very important topic from our unit 12 atoms, and that is the line spectra of the hydrogen atom. Now I know this topic can feel a bit tricky, but don't worry, just stick with me, okay? By the end of this session, I promise you'll find it so simple and you'll be absolutely ready for your exams. Chalo, let's get started.
Have you ever been walking down a street at night and seen one of those bright, glowing neon signs? Let's say a red one. Did you ever stop and think, why is it that specific shade of red? Why isn't it glowing with a full rainbow of colors, like a normal light bulb? Well, the answer to that simple question is actually the key to what we're learning today. It turns out every single element, whether it's the neon in that sign or the hydrogen gas we're about to study, has its own secret code made of light.
And this secret code, well, that's what physicists call its line spectrum. The easiest way to think about it is like a unique fingerprint. Or even better, the barcodes on products in a shop? It's exactly like that. Every element has its own special light barcode. No two are the same. So for today, our mission, our job, is to be detectives. And we are going to decode the secret barcode of the simplest element there is, hydrogen.
All right, so to crack this code, we need a simple picture in our minds. A mental model that will make everything, and I mean everything, crystal clear. So for just a moment, I want you to forget all the complicated physics, okay? Just imagine a simple staircase.
Believe it or not, this one simple picture, it explains the whole thing. Just imagine that the different energy levels inside an atom are like the steps on this staircase. Simple, right? An electron can stand on step 1 or step 2, or maybe jump up to step 10. But here's the important question. Can an electron just float in the air somewhere between two steps? No way! Bilkuni, right? It's impossible. And it's exactly the same inside an atom. Electrons can only exist on these fixed energy levels, on the steps. They can't be in the space in between. Got it? Samajh? This is the single most important idea you need to remember for this whole topic.
So what happens is when an electron absorbs some energy, it gets excited and jumps up to a higher step. But it's not stable there. It can't stay for long, so it has to jump back down. And when it does that, poof! It releases that extra energy as a particle of light, a photon, and that's the light we see. Now look at this diagram. It shows us how these different series of lines are formed. Let's start on the left. See all those jumps that end up on the first floor, n equals 1? That whole group is called the Lyman series. The energy drop is huge, so the light it gives off is ultraviolet. We can't see it with our eyes. Okay, now look at the middle group. All these jumps land on the second floor, n equals 2. This is the famous Balmer series. And this is the special one because these are the colors we can actually see. This is our visible spectrum. And finally on the right, you have jumps ending on the third floor, n equals 3. This is the Passion series. And this light is in the infrared range, again, invisible to us. So this staircase picture is fantastic for understanding the why, right? It gives you the whole concept. But this is a physics exam. And for exams, you need to be precise. You need to do calculations. For that, we need the master key, the one mathematical formula that can predict the exact wavelength, the exact color for every single one of these jumps.
And here it is. This, my friends, is the Rydberg formula. This is straight out of your NCERT textbook, so you absolutely have to remember it by heart, okay? It says 1 by lambda, that's the wavelength, is equal to r, which is a special number called the Rydberg constant, times 1 upon n final squared minus 1 upon n initial squared. Just look at it carefully. Trust me, for solving numericals from this chapter, this formula is going to be a best friend.
Now, don't look at the formula and get scared. Please don't. It's actually just our staircase story, but written in the language of maths. It's so simple. Look, Ni is just the initial floor, the step where the electron starts its jump from. And Nf, well, that's the final floor, the step it lands on. That's all. The only thing to remember is that for emission of light, the electron is jumping down, so the initial number will always be higher than the final one. You just put in these two floor numbers, the starting step and the ending step, and this formula will tell you the exact wavelength of the light that comes out. Simple as that.
Okay, let's put it to the test. Let's do a quick example to see how it works. Imagine the exam question asks you to find the wavelength of the H-gamma line. Now first, what does H-gamma even mean? Well, it's a code. The H stands for hydrogen. And for any series, the lines are named with Greek letters. The first is alpha, the second is beta, the third is gamma, and so on. So, H-gamma is the third line of the Balmer series. The moment you hear Balmer series, what should click in your head? The final floor, NF is 2. Correct. Now, since it's the third line of the series, the jump must be from 2 plus 3, which is 5. So our starting floor, Ni, is 5. We have our numbers. Ni is 5, NF is 2. We just plug them into our Rydberg formula. You do the calculation, and what do you get? You get a wavelength of 434 nanometers. And guess what? That's the exact wavelength for a beautiful violet light. See? The formula works like a charm. Perfect. Okay, everyone. Now I need your full attention for this next part. This is super important. We're going to talk about the silent killers. These are the common mistakes, the wrong ideas that so many students have, which make them lose marks in the exam, even when they think they know the topic. Let's make sure you don't fall into these common traps, okay? All right, here's trap number 1. Big one. You look at a picture of a spectrum and you see lots of different colored lines, red, green, blue, violet. And the first thought that pops into your head is, oh, this gas must be a mixture of many different elements. That's why there are so many colors. Wrong. That is completely 100% wrong. The correct exam-safe idea is that even one single element, just pure hydrogen gas, can produce all those different lines. How is that possible? It's simple. Each line is just a different possible jump. The jump from floor 3 down to 2 gives you red light. The jump from floor 4 down to 2 gives you green light, and so on. So please, remember this simple line. One element, many colors. Now, for the second major point of confusion. This one comes from thinking in the old classical way. The wrong idea is that an electron orbiting the nucleus would lose energy slowly, bit by bit, and then spiral into the nucleus, kind of like a satellite falling out of the sky. But think about it. If that was true, every single atom in your body, in this table, in the whole universe would have collapsed by now. The correct idea, the quantum idea, is that electrons do not spiral. They jump. It's an instant transition. One moment they're on step 5, the next moment they're on step 2, and because they cannot exist in that space between the steps, they can never spiral in. This is the real reason why atoms are stable. This whole idea of a quantum jump is what saves the universe from collapsing. Fantastic. Really good work, everyone. We've understood the main idea with the staircase, we've learned the formula, and we've also looked at the common traps to avoid. So now, let's just zoom out, take a look at the big picture, and summarize everything for a quick final revision.
You might be wondering, sir, why is this so important? What's the big deal with these colored lines? Well, the big deal is that these line spectra, these light barcodes we've been talking about, were the actual physical proof that showed Niels Bohr's model of the atom was on the right track. This was the evidence. And more than that, understanding these strange quantum jumps, this is your first proper step into the truly weird and wonderful world of quantum mechanics, which is what you'll be studying next.
Okay, so let's quickly list out the main takeaways for your notes. Ready? Point number 1. Hydrogen doesn't glow like a rainbow. It emits light only at very specific wavelengths, which we see as sharp lines. Point 2. These lines are not random. They are grouped into families or series, like Lyman and Balmer, based on which energy level the jump ends on. Point 3. Each and every line corresponds to one specific electron jump, from a higher energy stairstep to a lower one. And finally, point 4. The Rydberg formula is the magic key. It's the mathematical tool that perfectly predicts the wavelength for every single one of those jumps. Got it? So we have a really clear picture now. We know what is happening. We know that electrons are jumping between these fixed energy steps, and when they do, they spit out light. But this leaves us with one final and very deep question. Our whole explanation, our entire staircase idea, is based on one fact, that the energy levels are fixed steps. But why? Why are they like steps? Why isn't it just a smooth ramp where an electron can have any energy it wants? What law of physics forces energy to come in these fixed packets, in these discrete steps? I want you to think about that, because the answer to that why is our very next topic. And believe me, it is one of the most mind-blowing ideas in all of physics.